In this video, we are going to have some more solved problems from section 3.4 topics in algebra by Ian Hastane. Now, in the fourth problem, we have already seen that if R is a commutative ring and A belongs to R, then this collection A capital R, which is set of all small a R, where R range over capital R is a two-sided ideal of R. Now, we are asked to show by an example that this may be false if R is not commutative. So, if we consider suppose we take that R to be the ring of all rational matrices of size 2 cross 2, we know that this matrix multiplication is not commutative. So, we have this to be a ring which is not commutative, and we shall consider A to be this particular element in capital R. Then AR, when we compute, it will be elements of the form small AR. A is this 1 0 0 0, and any arbitrary element in capital R is taken as this. So when we multiply this, you have A with this, so you have A and then this with this, so that gives you B, and 0 here also 0, so you have these two to be 0. So my A capital R has elements of this form A, B, 0 0, 2 by 2 matrices with entries A and B from the field of rational numbers. Now, we consider X to be this AB 0 0 in AR. You, for the first case, you forget about this R. X you take as this. Then R to be any arbitrary element from capital R. Because we have used A, B here, we shall take A prime, B prime, C prime, D prime to be any arbitrary element in capital R. So when we compute this X into R, this is what we get. We have any element to belong to AR. For that, the condition required is the second row should be 0. And the first row element should be in capital Q. So all these being members of Q, you will have the whole lot to be in Q. This one as well as this. So definitely this belongs to AR. So our X into R is a member of AR. On the other hand, suppose I consider, so this is true for any R in capital R, XR is in AR, where X is in AR. Now on the other hand, suppose I choose my R to be particularly this. This is a member of capital R. Any element of this form will be in capital R. So in particular, we shall choose our R as this. Now we will compute our R into X. R is this and X is this. So when we multiply, this is what we get. We have this to be 0, this to be 0. So here 0, 0, and this one with this A, and this one with this gives us B. And such elements are not there in AR because the second row should be 0. So we don't have RX to be in AR, but XR is in AR. So AR is not necessarily a two-sided ideal if R is not commutative. Then in the next one, we have if U, V are ideals of R, then let U, V be the set of all elements that can be written as finite sums of elements of the form small u into V, where U range over capital U and V in capital V. We have to prove in this that this product is an ideal of R. So this is how the description of UV is. Collection of all summation Ui, Vi, where I range over 1 to n. Ui's are members of capital U and Vi's are members of capital V. Now, if we add any two elements, now first of all, we have 0 belonging to this, so this is non-empty. And we will consider separately two elements X and Y in UV and show that X plus Y is in UV. And if we consider some X to be in UV, minus X is also in UV. And then, so that will give that UV is non-empty and it's a subgroup under addition. And then we will prove that both Rx and XR are in UV for UV to be an ideal in R. Now, if you consider summation Ui, Vi and summation Uj, Vj, that we have finite sums, that is all. So when we add them up, this is what we get. It will again be a member of UV, so that this is closed under addition. And 0 can be written as 0 into 0. How many hour times that we want, we can have it. And next is minus. If we consider x to be this, then minus of x will be this. And that minus sign can be absorbed with ui, so that you can have, it can be clubbed with this. So you have minus ui, vi, and u, capital U being an ideal, this will be present in capital U. So we have this to be present in uv. So we have this uv to be a subgroup of R under addition. Now if we consider R into x, this is our x. So this R can be taken in and it can be clubbed with this. So we have this, and because capital U is an ideal, we have this to be an ideal of this. In the same way, x R, when we consider that R can be clubbed with this, and because V is an ideal, it will again be a member of U. So you have UV to be an ideal. It's a two-sided ideal. Now in the above problem, we have mentioned what that UV is. Now we'll show that this UV is contained in U intersection V. That is, elements in this are in U as well as in V. So that UV is contained in U intersection. Now since U and V are ideal, so any element in UV, when we consider, we know by the previous description that it should be of this form. Now you consider Vi being a member of V as a member of capital R, because capital U is an ideal, the whole lot will be in capital U. And the same way, this being in U, which is in R, so because capital V is an ideal, this will be in capital V, because capital V is an ideal. So we have this to be present in both U and V. So any element in UV is also there in the intersection. So UV is contained in U intersection V. Next, we have, if R is the ring of integers and U is the ideal consisting of all multiples of 17, and V is an ideal of R with the relation between U, V and R to be this, then we are asked to prove that either V is R or V coincides with U, and we are asked to generalize it. Now since R is the ring of integers under usual addition and multiplication of integers, and we know pretty well that any subgroup of Z under plus is of this form, generated by some integer M. Therefore the elements of both U and V should be multiples of some integers, say N and M respectively. That is U generated by N, say, and V generated by M, say. But U is given to be generated by 17, that's given. And we are also given that U contained in V, contained in R. That is also given to us. So this is the relationship that we have. The ideal generated by 17 contained in the ideal generated by M, contained in R. Now the relation between this 17 and the integer M is 17 mass divide N. So that will give that our M to be, because 17 is a prime, so M equals 1 or M equals 17. If M equals 1, then V is R. R is the ring of integers, so it is generated by 1, so we have V to be R. And if M is 17, then we have already taken U to be generated by 17, so your V will be equal to U. Now the same argument holds if 17 is replaced by any prime number P. So that is how we can generalize. So you will have P dividing M, then that M can be 1 or M is prime number. Same discussion, but with U generated by a prime N, prime P. Next one, if U is an ideal of R, prove that this collection is an ideal of R. All those elements of R which annihilate all the elements of capital U. What is U? U is given to be an ideal. If U is not given to be an ideal, then we cannot have this to be a two-sided ideal. Now let U be the given ideal of a ring R, and R of U be this collection. So description we have given. Then we have to show that it is non-empty. This subcollection is non-empty. And then we have to check the criterion for this R of U to be an ideal. So for which subgroup condition, and then Rx and XR should be there in R of U. So these are the things that we need to check. So we'll have to remember this DNC, that is D stands for the description. Whatever collection is given, that must be mentioned. Whatever is given to you in the problem, they must be written first, and especially the sub collection which you want to prove as an ideal, that must be written. So that description should be there, and you have to show that it is non-empty, and then criterion. C stands for criterion, and of course finally you will conclude that whatever you have given is an ideal. So R of your description you have. Now since 0 into U is 0, whatever may be your U in U, we have 0 belonging to R of U. Any element can be in R of U provided it satisfies this. We want our 0 to belong to R of U, which means 0 must satisfy this. That is 0 into U should be 0 for every U in U. That's true. So your R of U is non-empty. Next, under addition, it should form a group. So that means for two elements x and y in R of U, x minus y should be there in R of U. So that is criterion for subgroup. And then actual ideal condition is this. For every R in R and x in R of U, you have to have both Rx and XR in R of U. So the first one, because x and y are in R of U, you have both xu to be 0 and yu to be 0 for every u in R of U. That is how your R of U is described. Now we consider x minus y into u. By distributive law, this is xu minus yu, but xu is 0, yu is 0, so you have this. This is true for every u in R of U. So as the condition for x minus y to be in R of U being satisfied by it, it will belong to R of U. So you have x minus y belonging to R of U. Next, consider R in R and x in R of U. We have to show that both Rx and XR belong to this R of U, for which Rxu and XRu should be shown as 0. Now, because x belongs to R of U, x is 0 for every u in R of U. So if you consider Rxu, by associativity, you have this step, but xu being 0, you have R into 0, that is 0. Now coming to this XRU, you have x into Ru, you have x into Ru, associativity, and this Ru, because U is an ideal, Ru we shall take as some U prime to be in U. If U is not given to be an ideal, then this condition will fail. So, and this says that xu prime, but you have said that xu is 0 for every u in. So, in particular for u prime also it should be true. So, xu prime is 0. So, you have both xr and rx. If u is not given as an ideal, only this condition will be true. So, that means it will be only a left ideal but not two-sided ideal. Just because we are given u to be an ideal, it is that is R of U is a two-sided ideal. Otherwise, it's only a left ideal. Next, we have if U is an ideal of R, then this R colon U, which is set of all x in R, for which Rx belongs to U for every R in R. This is the description of this collection, sub-collection of R. Then we are asked to show that this is an ideal of R and that it contains U. Now, this ideal, after showing that this is an ideal called colon ideal, now first of all we see that it is a non-empty. Okay, we have got the description, so the description is here, but that must be written when you write the proof, and we have to show that it is non-empty, for which we show that 0 belongs to this colon R colon U, because if you consider R into 0, that is equal to 0, because U is an ideal, it belongs to U. So you have this to be an ideal. So, this to be a non-empty. And then when we consider x and y in this, we have to show that the sum and the inverse are also present. So if we consider this, then R into x plus y by distributive law gives us this, and because U is an ideal, we have this to be a member of capital U. That's true for every R in R, so that this is closed under addition. and the inverse exists in this way. R into minus x is minus Rx, and this U being an ideal, you have this to be in capital U. So that minus x is a member of this R colon U. Hence R colon U is a subgroup of R under addition. Next you choose R prime in R, then R into R prime x. So you will have to show that both R prime x and XR prime, both R prime x and XR prime are in the colon ideal, that is R colon U. So when can I, or how can I show that this is in R colon U? Only if I have R into that element is a member of capital U. So for which this is considered, and by associativity we have this R is a member of capital R, R prime is also a member of capital R, the whole lot is a member of capital R. So by the description of R colon U, you have this to be the whole lot to be in U. So that R prime x is in R colon U. Again, x belongs to this R colon U, for which suppose I consider Rx to be S. Because U is an ideal, we have this Rx, you have x to be in R colon U. So your Rx, by the definition, Rx will be in U for every R. So we shall take this Rx to be, for convenience sake, some S in U. So as U is an ideal, when we consider R into XR prime, this will be Rx R prime. This Rx is taken as S. So SR prime, because U is an ideal, this will be there in U. Our job is to show that R into XR prime to be in capital U. That is written in this way because of associativity, and this Rx is already there in U. So you have your this capital U being an ideal, it is in capital U. So R colon U is an ideal of capital R. And if you consider any small u in capital U, then because you are we want to have we consider x in U. We want to show that this x belongs to R colon U. Now if x belongs to U, let it be, we shall consider Rx. If Rx belongs to capital U, then your x will belong to R colon U. That is how we have the elements of R colon U. If we are able to show that Rx belongs to U, then we are through. But once you have x in R, x in U, for R in capital R, as U is an ideal, so we will have this to be in Rx to be in U. Because Rx is in U, by the description of R colon U, this x should be there in R. So conclusion is U is contained in R colon U. So this colon ideal contains this ideal U. So next we have for A in R, this collection RA to be AR. First we had in fourth problem, this is RA. Here see that R is not given to be commutative. So in that case what we can say is this RA is only a left ideal. So to prove that RA is a left ideal of R, we have to prove that it is non-empty. It's a subgroup, and for every R in R, A prime in RA, left ideal only. So RA prime should be there in capital RA. So a description that we have, non-empty we have to show, obviously 0, which is rewritten as 0 into A, is a member of RA, so RA is non-empty. And you consider two elements, A1, A2 in RA, so that A1 can be written as, remember here A cannot be changed, only X can be changed. So your A1 is X1A and A2 is X2A. So A1 minus A2 will be X1A minus X2A. By distributive law we have this step, and this can be taken as some X prime. So you have the whole lot to be of this form. this is a member of capital R, so the whole lot is a member of RA. So RA is a subgroup under addition. Now we'll consider R in R, A prime in this. Now you consider RA prime. This R into A prime is in RA. So we shall have that as, say, some X prime A or even X A we can have. So by associativity we have this. Your R is in capital R, X prime is also in capital R. So the whole lot is in capital R. That is denoted as some R prime. So you have this as such. So RA prime is in RA. So RA is a left ideal. We cannot have this to be a right ideal. So even in this case, description, non-empty criteria. Next we have the intersection of two left ideals is a left ideal. Similarly, we can show that intersection of two right ideals is a right ideal. And so intersection of two ideals is again an ideal in a ring R. So we shall have it for left ideal. Similarly, you have it for right ideal, and then conclude that it is asked for general ideal. Let U and V be the left ideals of R. Left ideal means basically they are non-empty and they are subgroups. So intersection of two subgroups is again a subgroup. So you have U intersection V to be a subgroup. We want to show only left ideal part. So you consider R in R and W in U intersection. Then RW, because U is a left ideal, RW will be in capital U, RW in capital V also. So that you have RW. This is not UW, it is RW belonging to U intersection V. It is RW and not this one. This one is not UW, it is RW. So U intersection V is a left ideal of R. Next, if R is a ring and A belongs to R, and R of A to be the set of all X in R for which AX is 0, then we are asked to prove that R of A is a right ideal. R is not a commutative ring. So we have R of A to be just a right ideal. So again, we have to have that D and C. D is the description, N non-empty because 0 belongs to R of A. You can write 0 as A into 0. So you have 0 belonging to R of A. So it is non-empty. And then criterion for it to be subgroup, for which X and Y in R of A, when we consider, you have AX to be 0, AY also to be 0. So A into X plus Y, when we consider, it is AX plus AY. Each one being 0, we have this to be 0. So R of A is closed under addition. Then for inverse A into minus X, we have minus AX. And because AX is 0, we have minus X also belonging to R of A. Therefore, R of A is a subgroup of R under addition. This is closed, and subgroup means we have to have both closure and inverse. Now we choose some R prime capital R. Then when we consider A into XR, we have that to be, see, we want to have this for R, this should be not R prime. You consider R in R, and then X in R of A, so that you can have XR, it is only a right ideal. So you consider R in capital R. This is not R prime, this is R in capital R. And when we consider, when we want to show that XR to be in R of A into XR should be 0. So for that we consider A into XR. So this is rewritten as AXR, and this in turn implies 0 into R, because AX is 0. So you have AX as 0 into R, that is 0. So that XR belongs to R of A. So that shows that R of A is a right ideal, but it is not a two-sided ideal. Now in this case, we have one ideal to be left, the other one to be right. Then can we have the intersection to be any ideal, that is either left or right or nothing. The intersection of a left ideal and a right ideal need not be a left ideal R. right ideal. For instance, suppose R is a ring of 2 by 2 rational matrices. That is, the entries are from the field of rational numbers. Now we consider this ideal U1, which is AR. We have this already we computed, and this is what we have. And U2 to be RA. So we know that AR, when R is not commutative, AR is a left ideal, and AR is a right ideal, and RA is just now we had RA to be a left ideal. Just now here RA to be a left ideal. If R is not commutative, RA is only a left ideal. So we have RA to be a left ideal, and this is a right ideal. So U1 is right and U2 is left. So intersection, when we consider, this is what we have. But this is neither a left ideal nor a right ideal, because when we consider any, this particularly this 1, 0, 0, this element when we consider, and this can be any element from capital R, in particular we choose this. So you get that to be this one which does not belong to you. And in the same way, we have to consider any element here as a 1, 0, 0, 0. And any element from R we can consider, that is considered in this way. When we compute that, this is what we get, and this is also not present in U here stands for this intersection. So it is neither a left ideal nor a right ideal. This is left ideal, this is a right ideal. This is right ideal, left ideal. Intersection is not neither left nor right. Next we have, if R is a ring and L is a left ideal of R, then lambda of L, which is this, is a two-sided ideal. So we consider now 0 is an obvious member. Description we have got 0 is an obvious member because 0 into A is 0 for all A in L. And closure with respect to addition and then the inverse, both are established for lambda of L to be a subgroup. So x and y in a lambda of L gives xa to be 0, ya to be 0. When we consider this by distributive law, this is xa plus ya, so 0 plus 0, you have this for all a in L. So you have x plus y belonging to lambda of L. So lambda of L is closed under addition. Next we consider this minus x into a. So that gives us minus of xa, but xa is 0, so you have this. So we have minus x in lambda of L for all x in lambda of L. Therefore, this is a subgroup of R under addition. Now we choose some element in capital R, and so when we consider R prime, see, our job is to show that for R prime in R and x in lambda of L. So if we consider R prime x a, R prime x a, it should be 0. So we have considered this, and this is nothing but R prime into x a, but x is a member of lambda of L. Our x is a member of lambda of L. So when we consider the product, x is a member of lambda of L means you have xa to be 0. That is why when we consider this R prime xa, which is by associativity, gives us this R prime into 0 that we have, and that is 0. So this is a member of this. Again, for x in lambda of L, when we consider this x into R prime a, this is x into R prime a. But remember, your a is in L and L is an ideal. L is a left ideal. So R prime a will be there in L. So you will have x into a prime, x into a prime. We want to have this one to be a member of capital L, and that is because L is a left ideal. If that is not given, nothing could be proved. So we have, because of this condition, this one we can have, and we have by the definition xa to be 0 for all a in L. So in particular for a prime also it should be true. So we have this. So that your xr prime is also in this. Therefore lambda of L is a two-sided ideal. So even here we have got the description, non-empty we have shown, and then criterion, one for subgroup under addition, and then the ideal condition. And the next one, if R is a ring, see, we know that whenever we are given phi to be a homomorphism, it takes identity element to identity element. Whenever we are given a homomorphism, we know that it takes identity element to identity element. So here we want to show that if we have R to be a ring with 1, and if R is a ring with unit element, and R prime is another ring with the unit element, say 1 prime, can 1 be taken to 1 prime? So the answer will be yes when we have this condition to be true on to in this problem, and in this case we need to have this to be an integral domain. So these two along with this. So if we have these conditions, then this could be achieved. 1 can be taken to 1 prime. Otherwise, we have only 0 being taken to 0 prime. Only 0 is taken to 0 prime, not otherwise. 1 will not be taken to 1 prime unless we have the condition given here is true. Now, since phi is onto for any a in R prime, there is one x in R such that a can be written as phi of x. So when we consider a, that is phi of x, is rewritten as phi of x into 1, which is because phi is homomorphism is written in this way. But phi of x is a. So you have a into phi of 1. So you have a to be equal to phi of x to be equal to in the same way. Here we wrote x into 1, here 1 into x. So phi of 1 into x. So phi of 1 a. So we have like this, a into phi of 1 to be equal to a equal to phi of 1. So it can happen only when phi of 1 is identity element with regard to multiplication in R prime. So that is, it should be unit element. If we denote that as 1 prime, then phi of 1 is equal to 1 prime. So if the identity element with regard to multiplication is denoted as 1 prime, then we have phi of 1 to be equal to 1 prime. Now in the next one, so here because of onto-ness we have this. Now the same concept for this, but in this case condition is different. Integral domain. R prime is an integral domain and kernel phi is different from R. If R is a ring with unit element 1 and phi is a homomorphism of R into an integral domain R prime with kernel phi not equal to R, then we have to show that phi of 1 is the unit element of R prime. Now if we consider phi of 1, we can write that as phi of 1 into 1, which is phi of 1 the whole square. So we have either phi of 1 to be 0 or phi of 1 should be equal to 1 prime. So if farmer was the case, then I of phi should be the whole of R. Because when we consider phi of 1 itself to be 0, phi of any element a will be 0. In that case, we will have the kernel of phi to be the whole of R. So that is not given. Therefore, phi of n should be 1. It is actually 1 prime we can have. That is the only possible case, and therefore 1 is taken to 1 prime whenever we have the given condition to be R prime is an integral domain and kernel phi is different from R. Thank you.